So look, it is wonderful to be here. What a distinguished audience. Paul Scully Power in the front row. And Hugh Durrant-White, who's here, is gone. Is he here, Marcus? Gone. But that was the most inspiring speech, and to be celebrating this iconic Australian and this story and looking to the future. I'm going to slightly change the narrative because we've talked about computers, and of course what computers did for society is establish the importance of communications. We had to somehow communicate, connect these computers, classical computers, or even quantum computers. And that deals with photonics research, which is my research. I'm the director of Sydney Nano, but I also have my own research group in the school that deals with photonics. So I'm going to take you on a photonics journey. Photonics in the new information age, faster, more bandwidth, smaller nanoscale devices, greener, more energy efficient, and smarter, which is starting to use photonics for sensors, for Internet of Things. And I'll give you some hints of what I'm talking about. So let's start right at the beginning. What is photonics? Well, I think we all here understand deeply what electronics is. It deals with controlling and manipulating electrons, and it is indeed the basis of all computers. And we're deeply familiar with Moore's law. Well, photonics very simply deals with controlling and manipulating photons, the building blocks of light. And arguably, photonics is as old as the laser itself. The term photonics was introduced shortly after the laser was developed, demonstrated, and the idea that we could transmit information in the form of photons, light waves, and that is indeed, as you all know, the backbone of contemporary communication systems. And indeed, in the 21st century, we're building a photonic chip that incorporates photonic elements to process with unprecedented bandwidths, not to replace CMOS logic, not to replace electronics, but to work in harmony with computing technologies to increase the bandwidth breathtakingly. So let's just step back and think about that history. I guess I always think, you know, it started with Maxwell's equations. These equations were introduced 155, 160 years ago, and these equations define, explain, govern electromagnetic waves. They are the most beautiful equations. I'll be lecturing on them tomorrow in the Slade Theatre for the second year physics students. If you're interested, come along. And of course, Einstein played an important role with his relativity, both special and general relativity. I'll come back to that in the early 20th century. The maser was introduced in the 1950s, and shortly after the maser, the laser, Mayman demonstrated he did not win the Nobel Prize. He should have won the Nobel Prize. The inventors of the maser did, Charlie Towne and his colleagues. And of course, the laser was for many years a solution looking for a problem. We had no idea how important the laser would be for communications, for medicine, for defense. Nobel Prizes, as I mentioned, but there was early on some thoughts on using lasers in medicine. Optical fibres were invented in the late 60s by Charlie Cow, who only recently passed away, working in Harlow in the UK. He was the first to imagine that you could take glass, draw it down by melting it to create a wire that could guide light. And he actually calculated that maybe you could transmit light from one side of the physics building to the other side of the physics building. He postulated that we could probably send a couple of megabits. So let's imagine, you know, what he would say now. Optical fibre communication started in the 70s. When I was a PhD student in the 90s, we were for the first time starting to deploy optical fibres between the major cities. And my PhD was caught up in that very exciting time. I went to Bell Labs and it was part of that revolution. Photonics was deployed in defence very early on. And in the 2000s, we see a new era of research that I'm going to explore a little bit over the next 10 minutes. The photonic chip, for the first time, really combining the paradigm of electronics with photonics, miniaturizing optical devices for communications, for radar, for sensing, for quantum technologies. Smartphone optics. We all have smartphones. The latest Smartphones have 3, 4 cameras. Some of the smartphones that are being designed have 10 cameras. The smartphone optics industry is actually $20 billion. Okay, there are more smartphone cameras on the planet than there are people. A really good example of photonics. And of course, photonics is used to make the smartphone. We use lasers to machine the housing, and of course, the backbone of the internet is all fibre optics. And gravitational waves, the detection was enabled by photonics. It was enabled by lasers and mirrors and photonic technology. So it's interesting to go that to a cycle of 100 years. So importantly, photonics is an enormously important part of our society, of our industry, of our economy. This is a report from the US National Academy of Science. It's about 6 years old. This was led by a number of academies in the US. We're undertaking a similar study in Australia, Simon Fleming, led by the Australian Optical Society. But this is a US perspective, but let's assume it's around 30, 40% of the global economy. The punchline is that optics and photonics is the linchpin of a $7 trillion industry. Now that doesn't say that the optics industry is in fact $7 trillion. It's probably around $500 billion. But if we did not have lasers, we would have no internet. So things would fall over. Optoelectronics, photonic technologies are critical in the IT sector, in banking, in biotech, healthcare, transportation sectors. It's an enormously important part of our global economy and our local economy. So what's really driving this investment, this industry? Well, fundamentally, it is the bandwidth explosion, which is fundamentally driven by Moore's law, the narrative we just heard from Andrew Zurak, increasing complexity in computers, that's allowing us to process more information, putting that information in our hands and through smartphones, that's allowing us to access that information. So let's just look at some factoids. Global mobile data grew 71% in 2017. We're talking about exabits of data per month. An exabit is 1 billion gigabits, massive quantities of data that are being transmitted, processed all around the world. Mobile data traffic has grown 17-fold in the last 5 years, and there are 650 million mobile devices that have been added. Well, in 2017, probably 1 billion mobile phones have been added to our world this year. And we're all accessing these amazing apps. During this presentation, Marcus Strom is probably going to tweet 4 or 5 times alone. It'll be retweeted. There are literally millions of tweets every hour. YouTube is consuming massive quantities of bandwidth, billions of email, Facebook, and I'm older that I don't even know what they're doing. Instagram, Snapchat, Tinder, Grindr. Sorry, I get lost. I mean, there's so much going on in that world. I live in Tampa now and I've got 3 kids. There are 27 portals in my house. It's out of control. And we've got the Internet of Things, okay, which is this big idea that smart devices, sensors are going to be connected. Already that is happening. It's sort of exciting, a little bit scary. And of course, in Australia, we have the National Broadband Network. Who here in the audience has NBN? Okay, for the people who put their hand up, are you happy with it? Really? Okay. Off the record, bit disappointing in the grand scheme of things. But look, it is exciting time and it is an absolutely essential part of our future to provide the bandwidth we need as an enlightened, modern innovation society. Looking globally, it's much more complicated. This is what the global optical fibre communications network looked like a decade ago. The story hasn't changed, but there are literally millions of kilometres of optical fibre that connect all the major cities. Every once in a while, we'll see a ship leaving Coogee, Botany Bay, and it's heading out to Fiji and it's putting out a new cable. These cables are literally that size. The fibre optic cable is the size of the human hair. It's surrounded by a jacket. There's power that needs to run along through that cable to provide amplification, and it needs to be thick enough that the sharks don't actually bite through the cable. That's true. So let's sort of think about the network. So I like to draw the analogy with the highway system. So these optical fibres are literally information superhighways. And the challenge really is that on the one hand, we have the bandwidth trunks, if you like, the backbone, but we also need to get the data on and off the highways themselves. It's sort of the analogy of driving out to the Blue Mountains, and every once in a while, you get to one of these spaghetti junctions. That's the router, and I have to slow down, I have to change lanes. That's where the traffic jams are, that's the bottleneck. And of course, this is exactly what happens. This is exactly the issue in those communications networks, and this is what we want to avoid. Okay? Now, there's something else that's happened that we didn't anticipate, and this is an important part of the narrative. I think Andrew hinted at this already. These apps, the Facebook, Google, YouTube, Twitter, require massive data centers. Where is all that data stored and processed? The data centers, they sit indeed in the Arctic Circle. They are the size of a small university campus. A massive amount of data is processed, tens of thousands of servers. These data centers are actually massive consumers of energy. They are a significant contribution to greenhouse emissions. Okay, non-negligible. They are more significant in terms of contributing to greenhouse than the airline industry, and guess which one is growing more quickly? Okay, we did not anticipate this 20 years ago when we were starting to imagine the networks, and this is requiring a completely new approach to how we design the devices that process the information. So what are we doing? I'll try to get to the point pretty quickly. This is an artist's impression of a table in a laboratory somewhere around the world, what I like to call the optical jungle. It comprises all the basic elements of any optical system: a laser, detector, an amplifier, a switch, a filter, a diffraction element. There might be some analog electronics, there might be an FPGA, there might be some storage. All of these components can be integrated onto a circuit. Using lithography, we talked about lithography. Those who joined me in the tour before, we know that lithography means printing patterns. We're printing patterns onto silicon circuits that allow us to massively reduce the size of these optical elements to the size of a thumbnail. So we get massive reduction in size, weight, power consumption. We get enhanced stability. We get the bandwidth, the photonics, the bandwidth that we've already benefited from through fibre optic cables. We also get low latency, and we get a revolutionary technology that's going to take us into the future. Now, what we're benefiting from here, and this is very much part of the narrative for the facility that we're standing in today in terms of our clean rooms, are the massive developments in silicon CMOS technology, the same silicon that Andrew and the quantum computing program at UNSW is building on, that massive industrial ecosystem that has over the last 40 years created these foundries around the world, such as Sandia National Labs, IBM in Taiwan, and here at Sydney Nano. So as mentioned, typical CMOS silicon wafers might incorporate literally billions of transistors. And so we have, for the first time, started to imagine photonic analogs, and companies like Intel, some of those major companies, IBM, have been developing photonic components, utilizing and leveraging silicon CMOS. And in particular, what is exciting for what we are working on here is that the most important building blocks of an optical system, the laser, the photodetector, the modulator, these are now compatible with silicon CMOS. We can build those components into a CMOS silicon wafer, into a chip, to create an entire optical system that is the size of a thumbnail. So to wrap up, photonic chips are part of our world. They're part of our ecosystem. They are transforming the internet. They are being built into data centers. They are providing ultra-high bandwidth, reducing the size, the weight, the power consumption, and they're smarter. We're utilising them also as smart sensors. My group is working with the New South Wales Government, the Office of the Chief Scientist and Engineer, to develop sensors that detect air pollutants. And maybe these sensors will be integrated into your smartphone, for example, to measure your health. We are developing photonic devices that are the basis of quantum secure communications technology. And we're working with, in particular, the defence ecosystem, microwave communication systems for electronic warfare, and I'll give you an example of that and we continue to develop ultra-fast devices for communications. We're very fortunate to be in this building, so we have a facility that has been designed deliberately to support the fabrication, the prototyping of these integrated nanoscale devices. You've seen some of the laboratories today. The facilities are absolutely breathtaking. We have 800 square meters of clean room space, and we have those basic semiconductor fabrication tools that we can use to print photonic circuits, the same tools that are used in the microelectronics industry. And so we really are still somewhat early on, a little like the narrative you heard from Andrew in terms of this paradigm shift as we start to imagine miniaturizing the photonic components to follow the same evolution that we've seen in microelectronics, to take these components down to the true nanoscale. Let me just summarize and wrap up with a couple of recent examples. First, to highlight some basic fundamental research. This is work from Dr. Andrea Blanco Redondo, who was a researcher in my group and more recently is a continuing member of staff in the school, and the Harry Messel Fellow, an outstanding researcher. And as part of a collaboration with the Technion, supported by the New South Wales Government, this project, we demonstrated for the first time a completely new regime of guiding light on silicon using so-called topological effects. Now, topology deals with the shape of structures. We often think about topography, but topology deals with the shape. And so a real paradigm shift in manipulating biphoton states, which is quantum states. And more recently, a demonstration of a new generation of memory using an interaction between light and sound, taking advantage of the fact that the speed of sound and the speed of light are different by 100,000 times. Rather than slowing light down, we actually transfer the information into a sound wave and store it in the sound wave, and that was published in Nature last year. My group also works with defense end users on next generation microwave technologies. This is work we're doing with the US Army Research Lab in Maryland, with Lockheed Martin and with Harris, who are defense primes. And the general narrative here is to develop a microwave filter that might be used to block a jamming signal. Okay, they don't tell me the details, but I think I know what they're working on. Might be part of a joint strike fighter. And we have developed a microwave filter that can tune from 1 to 30 gigahertz and well beyond that in a microsecond, and have extinction and precision that is unprecedented in any microwave technology. We've taken this overseas, we've deployed this in laboratories with end users, and there's an ongoing effort to commercialize this technology. So finally, I just want to thank my team here. That logo shouldn't be sitting on top of young Alvaro, but this is all part of a program that's supported by a wonderful ecosystem that we have around us in Sydney, with the New South Wales Government supporting the New South Wales Smart Sensing Network, the Department of Trade and Industry, the Office of Environment and Heritage in terms of the sensors. In the defence context, working with DSTO, the Air Force, Plaid Jericho, but also some of these US partners that we continue to work with. Thanks very much, and I enjoy talking to you today and showing you around afterwards. Thank you very much.